Okay, so let's get started. We're going to, for the next 3 or 4 weeks, we are going to look at vulnerabilities in smart contracts. So the first half of this course is more about the development side. And of course, when you start developing things, things can go wrong. And so the second half is how can you break poorly developed blockchain smart contracts. We're going to do this. We're going to go through some examples using this thing called the DASP10. If you've taken the web security class, we go through the OWASP top 10, which are the top 10 vulnerabilities in web applications. This DASP10 is the same thing for distributed apps. So these are the, and this is just someone's ranking, but most of the main ones are in this ranking. It's not a definitive ranking that like OWASP is, but this is one company's ranking of the top 10 smart contract vulnerabilities. Okay, so if you recall, Bitcoin had this very basic model of recording transactions. As part of just recording transactions, there was a scripting language that Bitcoin used to validate that, yes, these transactions are valid. They're from an authorized sender, the conditions are met to execute this transaction. So I didn't really talk about the scripting language of Bitcoin, but it's a very simple language that allows you to do basically assertions on the input to make sure that the transaction is okay. And so it has reasonable security. This scripting language hasn't had security issues associated with it, which is why when we're talking about smart vulnerabilities, security vulnerabilities, we're mostly talking about Ethereum. The language itself is what's considered non-Turing complete. And for those of you whose memory of what Turing completeness is fuzzy, Turing completeness means that you can compute any computable function with an infinite amount of time and an infinite amount of memory. Eventually, your language will allow you to compute any computable function in a nutshell. And of course, with a limited scripting language like no loops, for example, Bitcoin can't do that. The Bitcoin scripting language cannot. On the other hand, Ethereum supports a full Turing-complete language to implement arbitrary applications. And that was the whole point of Bitcoin, or of Ethereum. Buterin wanted to be able to treat the blockchain as a computer that could compute anything. And so this is why there are things like loops and recursion and all these things that a fully featured programming language that all of you are used to has, right? Like, computer science wouldn't be very much fun if all we had was a scripting language like Bitcoin. You'd be very few programs that you would actually want to write in that kind of language. And so for the last couple weeks, we've been doing Solidity, full-featured language, compiled down to EVM bytecode, full-featured virtual machine that can run this language. Okay, but imagine trying to hack Bank of America, except you can read all of their code in advance, all of your transactions are public, and if you steal the money, it's irreversible. This is basically the reality of Ethereum developers. Because in the blockchain, everything is public, and moreover, as soon as you publish your contract, it's immutable. That's the whole point of a blockchain. So this is the antithesis of what we're used to in the software world, right? So this is not something that, as programmers, at least I'm not good at it, like writing your very first version and having no bugs. But this is basically what you have to think about when you're deploying a smart contract, is you have to be able to deploy something with no bugs. Of course, everyone is fallible, and so we have programmed contracts that have led to over 400 million in losses. This is cryptocurrency losses, so who knows? It's funny money either way to me. But this is still a loss to people who actually have put in real money to invest in mining rigs, for example. They're paying the electricity bills, or they're taking their real money, exchanging it for cryptocurrency. If you have made the mistake of putting your cryptocurrency in the wrong kind of contract, you could be part of this $400 million loss. More than 30,000 smart contracts have known vulnerabilities in them. In fact, there's a Portland State student who is going through and auditing all the smart contracts on Ethereum right now. And yes.
I was just wondering, are those like active contracts with money in them? Or?
Yes, active contract. You can see all the contract creation events on Ethereum. And this particular student has, there's this tool called Mithril, which we'll talk about a little bit later in this class, which allows you to automatically analyze the bytecode of any smart contract and look for common vulnerable patterns. And so this is what, he's got a bunch of Google Cloud credits now, and he's going to just consume a bunch of resources to try and point Mithril to every single smart contract on Ethereum, just to see what this, and this is what others have done with different tools, which gets you this number. This is what they've done to generate that estimate. So you really, before you develop and deploy a smart contract, at least after, hopefully the people coming out of Portland State are aware that you really have to deeply understand the security issues. This is why I didn't want to offer a blockchain course without doing the second half dealing with security. Because you could, if you get the first half, you could think that yes, this is the way to go, and this is what, pushing out smart contract code is a good idea. But then the second half of this course, it should give you some pause before you jump on the smart contract train. If you do jump on it after this class, then you have at least an understanding of what's going on. So one of the most significant vulnerabilities or exploits that has happened is this thing called the DAO contract, which we'll cover in a couple of weeks. And this is a commentary on the DAO contract. And the DAO contract was written by some of the main Ethereum developers, right? These are the top of the food chain programmers, right? Like, they're way beyond me. And this is the commentary on this, following best coding practices, following the language documentation exactly. These are the developers who generated the documentation. It would have still remained vulnerable to attack. And so it's basically an issue where you have a programming language, Solidity, which is sort of introducing security flaws to the programmer that are basically hard to identify ahead of time. Okay, so some general issues before we get into the specific ones. We have problems that deal with semantic mismatches of the Solidity language. People are using Solidity because it looks like JavaScript. So JavaScript is used everywhere in web development. So yeah, you know what? For a smart contract language, let's use JavaScript. But we need other things that JavaScript doesn't have, so let's tweak the language. And these semantic mismatches of what you are expecting as a former JavaScript developer and what Solidity actually gives you is a problem. For example, numbers in Solidity, they're all ints, but in JavaScript, they're all floating points. So like, yeah, which one do you want? And if you write a number and you're expecting one, but you get the other, you have some flaws. So that's just one example. Common language features are misunderstood. I've tried to explain what these fallback functions are. I haven't even talked about low-level function calls, but Solidity has different ways of hiding complexity using higher-level calls. But if you're using the lower-level calls, you have to understand exactly what you're using before you put it in your program. You have data type problems in programming smart contracts. We talked a little bit about this when we talked about Solidity. We have lack of code audits to catch things like visibility modifiers. How do you make sure that those function calls can only be called internally versus externally? Lack of input validation to make sure only particular users can, or particular, like when you enter into a smart contract function call, making sure all of the parameters are what you think they should be. And then not error checking calls that you should be error checking. Another class of issues are Solidity or any high-level programming language basically obfuscating the underlying complexity of what's going on in the blockchain, and then the programmer not being aware of that, assuming that certain calls will work in a certain way when they don't. And so some examples of this. You can make a transaction as simple as a send. So from your wallet, you could say, oh, I'm going to call send. I'm going to send you money. And I'm going to return and do the rest of my code. But little do you know that that send could actually fail, right? And so if you think that the send is always going to work, but it fails, and you don't check the error condition, you've just lost some state on your smart contract. Things like time relative computation. So in Solidity, you can use the thing called now, a symbol called now, and that looks like a variable, but that's actually a function, because now is your current time, right? And it changes every single time you use it. So if you're treating that as a variable and and underneath it's changing every time, you could have some bugs introduced there. Okay. So the DASP top 10, this is the top 10 as it currently stands. We're going to go through every one of these, and we're going to go through them in the order of simplicity to the complex. So you'll see the first one we're going to do is bad randomness, because it's an easier one to start with. And then to teach you sort of these top 10s, I found this this really great CTF. I should say, so with this DASP top 10, they did some automatic analysis of around 20,000 contracts, and about 44% of them were vulnerable to one of these top 10 vulnerabilities. So to actually give you practice seeing the vulnerability and exploiting it, we're going to use the Security Innovation CTF, and I've organized your route through the CTF based on the top 10 issues that each one of these levels address. So the first thing I'm going to do is walk through the CTF itself, the mechanics of operating on this CTF. And I know some of you have already jumped in and started doing this, but I figured just to get on the same page so that all of us can start solving these levels, I'll walk through the very first lab, 3.1. Let me see here. So this is at a high level what we're going to do. This is D0 donation. So I'm assuming you've all done 2.1, where you've set up MetaMask and you've set up a Security Innovations account. So basically what we'll do is we'll go to the interface, we'll sign into MetaMask, we'll visit the site and the dashboard. We'll create an account and log in, so that should have been done before. We'll go to the dashboard, and then to deploy a level, and hopefully you've gotten some ether from the faucet so that you have money to deploy this contract, you'll click on this button, and by clicking on this button, you'll be sending 0.05 ETH to the CTF contract, and the CTF contract is going to call the level launcher to launch you a new instantiation of donation, and this instantiation of donation is only exploitable by you, is the idea, and the goal is to get that money out of the contract. So how does this work? The first thing that I wanted to talk about is this thing called CTF framework. Every single CTF level is derived from a base class called CTF framework. This base class, the only thing it does is control who can withdraw money from the contract. Because if you deploy your CTF level, I don't want anyone else to be able to solve and take your ether out of it. So you can see in this framework, you have this modifier called CTF. And you'll see this in the levels themselves, that they're going to use this modifier to make sure the only people who can access the functions are those who are authorized to play. And so authorized to play is this mapping that takes an address and says true or false. Can this contract access me? And if you look at authorized to play, it's just saying, in the constructor, it sets authorized to play to the CTF launcher. So every CTF level has a launcher contract. So by default, they're allowed to play. And then you. So when you deploy this contract, they use your wallet address and set it to true in this mapping. Now, you will see when you get to later levels of this CTF, you'll be deploying a contract to attack your level. If you deploy a contract to attack your CTF level, you have to add yourself to the authorized sender. You have to add the contract, the attacking contract, to this array. And so what you'll end up doing, anybody who is authorized to play with this CTF modifier can add any other address. So this will come in handy when we talk about heads or tails or lottery, which are two of the levels that I'm assigning you this week. When you develop an attacking contract and you compile and you deploy that thing onto the blockchain, before you initiate the exploit, you have to add the attacking contract's address to authorize to play. Okay? If you do not, then I saw this on the channel already, you get the out of gas error. So typically, almost all out of gas errors are because you haven't authorized the address. So let me get that out front, because this will save you a lot of time. This is where the last time I offered it, it was like people were spinning their wheels because of this all the time. Okay. So this is the first, the donation code, which is the first level we're going to look at. And if you look at this, you can see the constructor is a payable constructor, and it basically takes any money that it is instantiated with and then adds it to a fund balance. So the level launcher, so the donation launcher, is going to instantiate your smart contract with the 0.05 ether that you sent. Right? It's going to take the CTF game is going to take your 0.05 ether, say, you know what, level launcher, go launch this player's contract with 0.05, and then that gets added right here in the constructor. It also supports a payable fallback function, just in case you want to add even more ETH to the donation. And you can do this, right? Like if you want to send more money to this contract, you can add more money. Just know that anytime you add money to a smart contract, your level smart contract, your score goes down. So if you see the dashboard, it keeps track of your score. That is based on the amount of funds that are in your smart contract levels. So that's this part. There's also a function to withdraw all of the ether in this contract. And so if you call this, it will just transfer the funds to you. So this is not really a security vulnerability. This is just giving you the practice with the mechanics of working with this CTF is basically what this code is doing. Okay, so you can solve it, and I'm going to have you solve it in two ways in the code lab. The first way, the most straightforward way, is through MyCrypto. So the first thing you'll do is you'll go to the CTF level, and so when you click on the level, you get something that looks like this. You get a contract address, the game balance. You'll get these tabs, and one of the tabs, and the tab that you'll want to look for is the ABI, where you're copying the ABI over. You go to MyCrypto. In MyCrypto, you'll find the place where you're interacting with the contract, as I showed a couple of classes ago. You'll copy the contract address into the upper right. You'll copy the ABI into this window here, and then you'll click Access. And then you'll get something like this. And within the read and write to the contract, if you click on this drop-down, you can just click on Withdraw Donations from the suckers who fell for it. There will be several buttons that say, you know, generate the transaction, write the transaction, and then after a certain timer goes off, they'll allow you to send the transaction into the blockchain. You click on Send, and then it should ask the wallet, MetaMask should pop up this, saying, hey, do you actually want to send this? And then you'll click Send, and then you'll wait until confirmation, so you've seen this before, and then as soon as this thing has been confirmed, you'll see that if you click on that transaction, you'll get the transaction. So if you click on this transaction and then you expand out the transaction, you'll click on the transaction hash. You'll see that this thing is successful. And you'll see the transfer happening. So this is the level contract, and you'll see that the level contract is going to send 0.05 ether to your wallet address. as the person who sent that transaction. This is the screenshot I want you to take for every level that you solve on the CTF. This transaction that gets you your money back is the one I want, because I want to see your wallet address here over on the right, and then the transaction that goes to it. Okay. The other thing I want is when you go back to the CTF level, you'll see that the game balance is at 0 ether. Okay. Since I have extra time in this class, we'll just go through the mechanics very quickly, see how. And actually, if you have your computer, you could probably just play along. So this is donation. You play the game. I have 0.05 ether. I get to the ABI. I'll bring up my crypto. Connect up MetaMask. And then in Tools, I'll go to Interact with Contracts. And then I'll go to the level. Whoops. I have to log in again. I'll go to back to donation. I'll copy the contract address. I'll paste it. I'll go back and I'll copy the ABI. Copy it. Paste it. I'll access it. I'll select withdraw donations. I'll use MetaMask for this transaction. I'll allow it to, so you can tune the kinds of, so you can increase the gas price if you want the thing to go fast. So why don't I do that? So I want the thing to go fast. And then I'll write the transaction. I'll generate it. I'll send it. It'll bring up this MetaMask thing. And I can send that. And I will confirm. And then we will wait. And hopefully not too long. View this thing on Etherscan. Right there, the contract address, the ABI.
In the top right corner. I'm not seeing the MetaMask.
Up here? Wait. So you have to, oh yeah, you set this to, if you go to Tools and Interact with Smart Contracts first, and then in the upper right, yeah, I have this set to Ropsten. It might not be Ropsten by default, but usually Ropsten Auto is what you can use. Yeah. I can look at that after this is done. Okay, and then you get the success, and then you can see the 0.05 transfer. This is the screenshot I would want. You would go back to this, and there's usually a pop-up that says you're a winner. This is the other screenshot I want, where the game balance is 0. Okay, so that is the hello world of the CTF. So hopefully, well, you can get started. But I'm actually going to do the very first of the top 10 now. So.